We want to see how hard do we have to push just to prevent, or what's the lightest we can push, such that the crate does not fall down or slide down the inclined plane. So the minimum applied force to prevent it from sliding down the plane. In both situations, we have a coefficient of friction equal to 0.25 between the crate and the plane. We have that 30-degree incline, and the crate has a mass of 50 kilograms. In the free body diagram here, I really just have one object I need to look at, and that's the crate. I'm isolating the crate, so I'm removing the surface that it's resting on. But I will include just this construction line to help me write equations out of this. On the crate, I have one applied load, that force P, which in this case is completely horizontal, or it's along what I'm calling the x-axis. And what are the other forces that act on my crate? Right, the weight force and the normal force. The weight force, the gravity will always be pulling it towards the center of the Earth, which I'm designating along my y-axis. It has a mass of 50 kilograms, so the weight of the crate will be 50 times gravity. So 491 newtons is the weight force. And the normal force will always be acting normal to the surface of contact. In this case, that's a 30-degree angle. So the normal force is not up. The normal force is going to be at this angle that's normal to the interacting surfaces. So that's some normal force. I'll just call it lowercase n, so I don't confuse it with newtons. And because it's normal to this surface that's 30 degrees from the horizontal, this is going to be 30 degrees from the vertical. Or I could say 60 degrees from the horizontal. Either way, I'm going to get the same result. Weight force, normal force, and an applied force there. And then what other force is going to be impacting the crate? Right, this is a friction problem, and we're looking at static friction. So in scenario 1, along what direction should our friction force be acting? Right, it should be, in this one, the crate, we're pushing as light as possible so that it does not go down the plane. So in this case, it wants to go down the plane. We're pushing to counteract that. Because it wants to go down the plane, the friction force is going to be acting against that direction. So the friction force is going to be up and to the right, but parallel to that surface. Normal forces are going to be perpendicular to the interacting surfaces, and frictional forces are going to be parallel to those interacting surfaces. But we do need to know the direction. The normal force we know has to be pushing up on the crate because the ground can't pull on the crate. But potentially the friction force could be going up the plane or down the plane. But in scenario 1, we know it's pointing up the plane. We use this now to get our equilibrium equations. Right now we haven't said anything about it's on the verge of slipping or it's actively slipping. Really the only assumption we made here is that in the absence of friction, it would slide down the plane. And that will be different from scenario 1 to 2. Again, we're presuming equilibrium here. So I'm saying that I'm not accelerating, so my sum of forces is equal to 0. In the x direction, I have the applied force P. I have the horizontal component of my friction force, which as I've drawn it will be plus Fr cosine 30. And acting to the left, I have n sine 30. I have 3 unknowns here, P, Fr, and lowercase n. I can make equations for the y direction. Here I have all of my weight force in the negative y. I have Fr sine 30 in the positive y, and n cosine 30 in the positive y as well. As I was saying, because we don't know any of the heights or anything like that, I can't do a moment equation. So 2 forces, x and y. And if I look at the 2 equations I still have between the two 3 unknowns. So from the equilibrium equations, this is not yet solvable. I have 3 unknowns, but only 2 equations. But I'm done making equilibrium equations. So now the new step is away from the free body diagram, I have to consider the ways that this is going to move, or I have to consider what am I testing. In this case, I'm testing what's the lightest I have to push on it such that it's not going to slide down the plane. So this is a situation we're seeing, we want to push just hard enough that it's not moving, but if we pushed any less, it would start to slide down the plane. So the additional consideration here, I only have one scenario, I'll call it A, is that it slips down plane. And we'll get to cases where we have multiple ways it could move. This is the only way this one would move. So this is where we get those extra equations, is from these different conditions of how the motion could occur. So because we're considering when it's just, and really this is just on the verge of slipping down the plane. When it's just about to slip down the plane, that's where I can say that the force of friction is at its maximum value, which is going to be the coefficient of friction mu times the normal force between the crate and the ground, which I've been calling small n. For these surfaces, my value of mu is 0.25. So for equation 3a, I get that the force of friction is equal to 0.25 n. Again, it's equal only when it's just about to slip. Now if I look at equation 1 and equation 2, and now equation what I call 3a here, I have 3 equations, and I still only have 3 unknowns. So between those 3, I now have a solvable system of equations. So for example, if I put 3a into 2, I can replace FR with 0.25 times n, put it into here, and now equation 2, the only unknown I'm going to have is the normal force. So in this case, I know that the normal force is going to be equal to 495 newtons. Again, I want to note, the normal force is not equal to the weight. Actually turns out to be fairly close, but never assume the normal force is equal to the weight. You must solve for it using these equilibrium equations. Since we know the normal force is 495, we can find the force of friction by putting that back into equation 3a. The force of friction would turn out to be 124 newtons, which we're not too concerned about in this one, because really what we wanted, well, we need these now to go back up to equation 1. I know the force of friction is 124. I now know my normal force. So putting this information into equation 1, I find that the force that I would have to be pushing with, such that it was just about to slide down the plane, is a force of 140 newtons.